In this session, we are going to study about forced harmonic oscillator. Oscillations, as you know, are generally damped. So to avoid damping, we provide periodic force from outside so that the oscillator oscillates with constant amplitude. Such an oscillator is called forced harmonic oscillator or a driven harmonic oscillator. So the equation of motion of a driven harmonic oscillator is F net is equal to F spring plus F damping plus F external. Now F net, we know, if we take a spring bound system, F net is m into d square x by dt square. F spring is minus x and F damping is minus b dx by dt, and F external is the periodic force that we apply. Let it be F0 sine omega Ft. Omega F is the angular frequency of the external periodic force. Rearranging, we get m d square x by dt square plus b dx by dt plus kx is equal to F0 sine omega Ft. Dividing toward by, we get d square x by dt square plus b by m dx by dt plus k by m. X is equal to F0 sine omega Ft, where F0 is capital F0 divided by m. I am going to replace b by m by 2 beta and k by m by omega 0 square. So I get d square x by dt square plus 2 beta dx by dt plus omega 0 square x is equal to F0 sine omega Ft. So this equation represents the differential equation of a forced harmonic oscillator. Now we can solve this differential equation. Now since the right hand side is not equal to 0, x has two values. X has two values, one corresponding to particular integral, another corresponding to complementary function. To find the solution corresponding to complementary function, we equate the differential equation to 0. That is d square x by dt square plus 2 beta dx by dt plus omega 0 square x equal to 0, which is nothing but the differential equation of a damped harmonic oscillator. The solution we know, x of t is equal to a e raised to minus beta t sine omega t plus 5. So this is the solution corresponding to complementary function. To find the solution corresponding to particular integral, we assume the solution of the second order differential equation of the form x of t is equal to af sine omega ft minus theta. Take d square x by dt square dx by dt and x, when substituted in this equation, we get minus af omega f square sine omega ft minus theta plus 2 beta AF omega F cos omega Ft minus theta plus omega 0 square AF sin omega Ft minus theta equals to F0 sin omega Ft. On the right hand side of the equation, to the argument of sine, add theta and subtract theta. So what you get is F0 sin omega Ft minus theta plus theta. Take this as A and take this as B, and expanding using the identity sin A plus B, we get F0 sin omega Ft minus theta cos theta plus sin theta cos omega Ft minus theta. Multiplying through by F0, we get F0 sin omega Ft minus theta cos theta plus F0 sin theta cos omega Ft minus theta. Equating the coefficient of sin omega Ft minus theta and cos omega Ft minus theta, we get, when you equate the coefficient of sin omega Ft minus theta and cos omega Ft minus theta, we get these two equations. Now, rewriting this equation, we get AF omega 0 square minus omega F square is equal to F0 cos theta and 2 beta omega F AF is equal to F0 sin theta. Squaring LHS RHS of this equation, squaring LHS RHS of this equation and adding together, you can write steps AF square omega 0 square minus omega F square the whole square is equal to F0 square cos square theta and 4 beta square omega F square AF square is equal to F0 square sin square theta. Adding these two equations, we get AF square is common term, omega 0 square minus omega F square the whole square plus 4 beta square omega F square is equal to F0 square, because sin square theta plus cos square theta is equal to 1. We can rearrange for AF is equal to F0 divided by root of omega 0 square minus omega F square the whole square plus 4 beta square omega F square. So this is the expression for amplitude of a forced harmonic oscillator. The phase angle theta can be obtained by dividing these two equations, that is F0 sin theta is equal to 2 beta omega F AF and F0 cos theta is equal to AF omega 0 square minus omega F square. So on dividing these two equations, we get tan theta is equal to 2 beta omega F divided by omega 0 square minus omega f square, or theta is equal to tan inverse 2 beta omega f divided by omega 0 square minus omega f square. So the complete solution of this differential equation is complementary function plus particular integral. This is the solution corresponding to complementary function, and this is the solution corresponding to particular integral. We know as time progresses, this term will be becoming to zero value, and after some time, after making few oscillations, this will retain, or in other words, the forced harmonic oscillator will be oscillating with a frequency which is decided by the frequency of the external periodic force.